Hello. Welcome to this strange talk where we solve all of life's problems using only ray marching and stupid rendering tricks. I'm Tom, and I'm half of a new indie game studio called Palmslight, and we have recently released our first game called Tiny Glade. In case you haven't seen it, here's our trailer. So it's a little cozy diorama doodling game where you just build things for your own enjoyment, making cozy cottages, romantic ruins, and lovely castles. There's no goals, there's no stress. You just kick back and enjoy yourself making something pretty. And one of the promises of the game is that whatever you do, the game will make beautiful by its rendering and procedure generation. Okay, but we're here to look at graphics. So from the graphics nerd angle, the game essentially does doodling, so like MS Paint style, but with procedure generation. We have hundreds of thousands of individual objects with malleable geometry and dynamic time of day. But the audience is casual, therefore the hardware is like often 10 years old, so we have to run a kind of potato devices. And to pull this off, we have crafted like a custom engine on top of Vulkan, Rust, and Hazel SL. It is mostly written from scratch, but using tons and tons of open source software and some of our own secret sauce. But nobody actually works on full-time on rendering in our game, besides me doing kind of long night shifts and not knowing the separation between work and life. So it's going to be a lot of jank warning and things kind of like, if you think I'm saying something wrong, it is wrong, because we didn't really have time to properly research things. Because the team is super tiny. It's Anna, Para, and I, and so we have collaborated with Uda and Martin from Knock Knock Audio for the game's audio. So you might be wondering, why did such a tiny studio decide to make a custom engine? And the story of that is kind of connected to where it all began. And it started as a side project by Anna. And it was a hobby project for about a year before it turned into a game. And only joined after that 1 year. And within that time, it was a hobby thing to learn rendering. So Anna was quite versed in procedural generation offline, but she wanted to learn rendering and actually try to do procedural in real time as well, using compute shaders and all the stuff that we all love. And the whole thing started with just one wall generator that was placing bricks procedurally. Then the whole thing turned into multiple walls, arches, terrain, and so on. And after a few months, it kind of got this moniker, tiny building game, and a lot of people got enthralled by that. And the things they fell in love with was the kind of very gradual or granular procedure generation and the organic nature of it. So at that time, some of the elements of that were already set in stone. That we had this like tons of individual bricks and so on, and every pebble and plank were unique. And that was fine initially because this is the first announced trailer we had for the game. As you can see, there was like not much complexity, just a few buildings. And maybe 1,000 bricks. But it had to scale. It would scale a lot because the more we streamline the UX and the more we optimize things, people just kept building crazier and crazier things. Some people just don't accept the tiny part of Tiny Glade, and some of them are just fine working for like 10 FPS all the time. So builds get crazy. This is just a few samples of what the community has created. This is still on the same side, just like lots of beautiful things. Different kinds of aesthetics. Some people just decide to build entire towns or even fragments of cities in the game. Just comparing to the initial shots, this is completely bonkers. Oh yeah, some people just recreate parts of Lord of the Rings because why not? And running into the limits of all the instances we have in the game. All of those are individual bricks, by the way, just we need to render separately. And some people just like, okay, cool, it's a dueling app, I'm gonna make something funky. And like just making things we never anticipated. And by the way, we don't have indoors in the game, so all outdoors. People just have figured out how to still make indoors work somehow. So it's UGC game for you. So how to deal with it? Well, we have tons of geometry to somehow make it appear. So we employ GPU-driven rendering for that. So the reason is that, just like at the start, our generators don't synthesize meshes. We don't deform geometry to any fancy skinning. We just generate tons and tons of individual bricks and planks, like hundreds of thousands of them. And similar for tiles and pebbles and potted plants and window shutters and so on. Everything just comes out of little bits. Well, GPUs are way better at dealing with the crazy amounts of stuff. Therefore, we do it on the GPU. But before you create a code rendering system, you have to name it, right? So everyone does that these days. But Nanite was already taken, so ours is called Nani. And what Nani does is performs GPU-driven culling, sorting, LOD, and draw generation. We don't use clusters of any of the new fancy stuff because our meshes are way too simple for that. Like our plank or brick would be just like one cluster probably. And we don't use mesh shaders because our min spec doesn't support them. But we do have one pretty simple scheme that we just like put all the geometry data for a single material into the same vertex buffer, and we can render any mesh from that using just sub-slicing from that index buffer. And for example, changing to different discrete LOD just becomes a +1 to the index in the mesh array, or in the atlas. And in terms of calling, it is by now pretty standard stuff that was already covered at the conference today, a few days ago, which is the 2+2 pass occlusion calling, introduced, I think, by Seb Altonen and kind of popularized by Nanite. We render a first pass where we draw everything that was visible in the previous frame that we can now do to stable mesh IDs between frames. Then we build a depth pyramid, and then we detect what we had missed, render those objects, and then rinse and repeat. So that is pretty standard. And then in the simplest path, once we have determined what is visible, we can just potentially just add every object to a separate draw list. And the simple path essentially has one draw list per material and mesh type. We just add an increment integer. We draw right to an indirection map. And then we can draw everything using a single draw index indirect. And because all the meshes for a single material are packed into the same mesh, or like a vertex buffer, we can draw essentially all of the meshes of a single material using a single draw index indirect. So the draw count, number of draws is the number of meshes we have, so we can use the correct subslice of the index buffer, and then the number of instances in each of the generated draws is just the number of visible instances. So pretty simple stuff here. And that works well for bricks, because for them we need something with very low overhead, since we have up to 1 million of them, and we're going to be extending it to up to 2 million soon. But it's still flexible enough that you can actually do some pretty cool stuff, like for the last LOD for bricks. We actually have a model which uses just 6 triangles, which is like half a cube, that we flip the vertices to actually make them always front-facing, and that's the pixel shooter essentially becomes just a dispatch mechanism for ray marching, or in this case, analytical intersection with a chamfered box, so we can synthesize little bevels around the edges and make sure that even far away we can catch lights on those kind of thin lines and get a similar look to what we have with the full mesh on top. But not everything is so simple. For example, our trees, they use a scheme of expanding billboards from geometry. And that scheme introduces a bunch of overdraw. And on top of that, we also have depth writing in order to break up the detail, actually make it appear like we have individual leaves. Which means that the whole pass becomes more overdraw heavy, and we need to do something more. And if you have something like this, you really want to sort things front to back. But even with a simple scheme, with our system, it's pretty simple to do that. So we use approximate sorting by just binning things into a number of buckets. We use 1024 and essentially do a single pass radix over the visible meshes, or a counting sort, if you will. So we insert the meshes, or the visible instances, in the correct place based on the depth slice. Then we end up with a single list, which is approximately sorted. And once we have that list, we can generate draws from it. But because it is sorted roughly from front to back, it means that sometimes you have meshes which are different. So you have to switch which mesh you're drawing in between. And to strike a balance between sorting and number of draws what we generate from it, we process the instances in groups. And in each group, we generate a mini histogram of which meshes are actually visible, which means that if you happen to have the same mesh and just, say, 32 instances of them, you issue just one draw from that. But if you have a mixture, you do as many draws as you have meshes within the group. And you can kind of fine-tune just how much sorting you get and how many draws you generate by just changing the group size in that process. And then it also means that, just like with the previous scheme, we can draw essentially everything using a single, in this case, draw index indirect count, which means on the CPU side, it is still very cheap. And in terms of the win this gets us, for the sort approach for the trees on the chunky GPU, it's roughly 65% of the render time compared to the unsorted. And in general, it seems to be a bit faster on AMD at least, but we're still kind of looking into it and figuring out what works best, because we discovered that like pre-Turing NVIDIA cards actually have a pretty bad tax on the indirect count, because you have to provide the maximum number you can provide, and it seems to just spam the command processor of the GPU, and you end up paying a pretty hefty tax. And you look at the GPU profiler, and it's just like sitting there and sleeping. So still figuring out the best approach here. And in terms of deferring stuff, this is not as neat as something like a VBuffer approach like Nani we use, and probably wouldn't scale to thousands of materials, but we don't have thousands of materials. We have just a handful of handcrafted materials, and it ends up being good enough for us, partially because we can kind of roughly know at the material stage in which order things should be drawn. Like we know that grass will usually not include buildings, and trees will tend to include buildings, and so on. So we can kind of just do a classic pre-sorting based on materials. And it just happens that our gbuffer is very thin, so we can suffer some overdraw. And speaking of gbuffers and lighting, they usually plug into lighting. So let's talk about lighting, or starting with the lack thereof, which is shadows. The most important light source we have is the sun, and we knew from the start that it would be soft. So we look at the most attractive entry into it at the start, which is moment shadow mapping. And after some initial tests, we have determined that the game seems to be a worst-case generator for moment shadow maps. If you use VSM, you might have seen something like that, which just gets this kind of leaking whenever there's multiple depth layering, and MSM is supposed to fix it, but we have found that because of the freeform nature of the game and the UGC of it, people will just create scenes that will create this kind of artifacts. So we can really go with MSM, as nice as it would have been. So we had to go with PCF that we all love and, well, I guess, know and hate, I guess. It does work in general, but requires lots of bias tweaking. But we can mostly get away with the normal offset bias and just lots of hand tuning of the whole thing. And then we just throw a pretty standard PCSS contrast sharpening on top of it. However, if you implement shadows with even synchronous softness, and you do all of your biasing well, you still end up with something like this. And in our game, we have continuous time of day, and you can also change the time of day as you like, and you end up with this kind of horrible aliasing. So unless you have enough shadow map resolution, and you rarely do, you'll end up with this artifact. However, if we see something like this in the primary visibility, we typically throw it at anti-aliasing, right? So why don't we do it for shadows? And TEA specifically is really good at dealing with kind of temporal aliasing. So typically in TEA, you would take the new input you have just rendered, you combine it with history that you rectify, modify, or reject in some way. And you do that by estimating some kind of statistics from a local neighborhood of the new input, and then clamp to those statistics, for example. But if you do it in screen space, it will not do anything, because the features that are flickering are larger than that tiny 3x3 kernel you would throw at it. So what you do instead is you derive those statistics from the actual space in which the content changes. And in this case, it is the shadow kernel. In the shadow map space, that is the exact resolution or the frequency at which you need to offset and find your neighboring samples. And the nice thing about it is that you're already likely fetching all of this data for your PCF kernel, so you actually don't need to do anything special. Typically, when calculating self-shadows, you are essentially doing a mean estimator, which is the first statistical moment. If you also track the second statistical moment, you can calculate the variance from that. And then borrowing from Marcus Salvi's variant-based TAA, you can calculate a bounding box for clipping the history, and thus you can essentially apply TAA to history as well, TAA to shadows. You end up with a small slight artifact, and that's in areas of high variance, you can have ghosting, but that's also pretty easily fixable because the largest areas of variance will be in very soft shadows, and those are less prone to aliasing. So you can just shrink that box, and you can control the size of the bounding box based on the shadow softness. And if you combine all of that together, you can end up with shadows something like this from the same resolution of shadow map data. So you can still see a little bit of flickering, but it's generally much more stable, even softens some of the motion of like the flag waving and so on. But this is still not sufficient resolution, and unless you have the budget, you cannot really crank up your shadow map resolution to the point where you get all the fine details. And that is something that has been fixed in post in recent years. It dates back, I think, all the way to Crysis 2. But the idea is generally is that you ray march towards the light source, and then in the screen space you can detect whether you actually intersect something, and then claim that to be a shadow as well. And there is, in our case, we just do a simple ray march using just like a shader we use essentially for all of the ray marching, but there's also a solution that has recently been quite popular from Ben Studio. We tried it as well. I have a comparison, but we also found that our approach was a slightly better fit. And just for comparison, this is what we get with no contact shadows in a pretty extreme case where the sun is just like grazing the building. That typically you just get like kind of just blurriness and nothing cool. And if you just add 3 taps of ray marching, suddenly all the detail pops and looks like, oh, you've actually just added geometry. So that was kind of fun to see. Like, we actually had to shrink the bricks a little bit because they were sticking out too much because we were overcompensating previously. And then comparing that to the Ben Studio version, you actually get slightly better detail resolution with their approach. But we found that we can get the same if we just increase the number of taps on the ray marcher just a little bit, and having the control over how many taps we have, and having also the ability to potentially move them, shoot them at an angle to get soft shadows was a win for us. Also, nice thing is that compared to the Ben Studio version, ours is fully stable as well if you zoom in and out, because it doesn't have that dispatch restrictions. But if the other approach works for you, then that's cool. But if you try to implement ray marching, you'll quickly run into this kind of issue, which is just uncontrollable acne that just doesn't look good and ruins your day. If you don't apply any bias, you're just going to have a bad time. If you apply some bias, you'll probably still have it. If you apply a lot of bias, you remove all of the detail and still end up with kind of what we started with. And then if you look at the same thing from a different angle, it turns out you still haven't removed bias, and you end up fighting the same war as you had with PCF self-shadows. But what if I told you there's a thing you can do to remove pretty much all the acne and keep all of the detail? So this is comparing to the no bias version, and even behaves itself smoothly in temporal cases. So it's going to be weird, because so your parents told you not to sample depth maps using linear samplers. Well, listen to them, but also don't listen to them. Let me explain. So if you point sample shadow maps, you end up with this kind of like Duplo/Legoland at the micro scale, where the stair steps between samples create this kind of sharp edges, and you end up hitting them accidentally, and this is what the acne comes from. And biasing essentially just offsets that ray from the geometry, which also removes interesting detail. But if you use a linear sampler, you can reconstruct the underlying geometry. But so why don't we just use linear samplers for our depth? Well, because not everything is continuous, and the linear sampler will pretend that everything is going to shrink wrapped, and everything is a continuous surface, and you're going to have false hits, which create their own artifacts. But what if we use both? I know it's weird, but if you fetch both the linear and point sample data, and then for the intersection test, you use the furthest of the depth values, and for the thickness check, you use the closest of the 2 values, it just happens to work. I can only hand-wavingly explain it because I was messing with things and I managed to stumble upon it, and it just happened to work too well, and I was kind of misbelieving. So maybe there's a reason it works, maybe it doesn't. I don't have time to dig into it, but the kind of hand-wave explanation is that the false hits the quantization or the third stepping are gone because you're essentially cutting up the corners by taking the fusion of those two. And then the discontinuities are gone as well because you're reintroducing the vertical lines as well in the function you're intersecting. And those vertical lines allow the ray marcher to detect misses, which is further helped by using the larger of the estimates for the thickness calculations. But honestly, I don't really get it. So if you want to grab it, we are sharing the source code on Gist, so you can try it yourself. We use it for all of ray marching in the game for all sorts of effects. One of the things we use it for is lookalikes as well. We haven't implemented anything fancier, just essentially through the same ray marcher at them. And so because it is quite flexible, you can just do a classic thing of for loop goes blur and intersect all the lookalikes, ray march towards them, and we have shadows from lookalikes. And it's something we're still investigating. Because of the UGC nature of the game, we end up having thousands of lights or hundreds of thousands of lights potentially. So I'll need to look into restore DI. For now, it's kind of simplistic, but it gives you the idea that you can get local stuff as well. The other most important light source that we have is the sky. And we didn't go for any fancy atmospheric scattering model because we wanted to have all the control. Our game is not meant to be photorealistic, so we just threw a bunch of blurbs together, handcrafted some timelines, and for each of the levels that we have, we made skies that just look nice from an artistic point of view. And then our clouds are just a bunch of sprites scattered on a cylinder. And then we have pre-baked some lighting using a bunch of spheres together and then painted over a little bit. That's done in Houdini. And then we blend with the different textures depending on some of the angles of the light, depending how it hits the sprite. So we have a few versions for him from a few different angles. It's like a standard trick used in lighting of particles in games. But the cool thing about the sky is that it becomes a light source for our global illumination. So let's talk about that. Let's talk about global illumination. When we started, Tiny Glade was going to be quite tiny and flat. So we didn't have any of the fancy shape layering. We didn't really have buildings. We just had some walls. And the first implementation of our GI was using a technique from like 21 years ago now from MotoGP, where you essentially render a top-down map of lighting, and then you sample that for every pixel, and you have approximation to lighting. We had a slightly fancier twist in that, which was shooting rays from a cone and kind of approximating where it would intersect the height map. And it was giving us something. It was not completely terrible. It was a little bit of fill light, I guess. But when we actually had a bit more layering of shapes, it became pretty clear I wasn't going to cut it. It was kind of just making those cold scenes that didn't really make sense. And it will be a while until we figure out exactly what was missing from it. And to do it well, in general, like in global illumination especially, you have to start with reference mode. Because even if you cannot eventually match the reference mode, it's very important to have it on hand and know whether when you're tweaking something, whether you're actually making it better or making it worse. Like, should you have more AO? Should you have less AO? Should we tweak this filter that way or this other way? And it's sometimes very, very hard to tell whether it's all fine or whether you're completely off with it, just like you saw with the picture earlier. So ideally, you would just add a path tracer straight to the game, and ideally then verify it against something that well-known and good like Mitsuba, and then carry on from there. And sometimes screen space is enough potentially depending on the game, but sometimes it is not. In our case, it was not going to be sufficient because of the layering of shapes and some people doing indoors. So we considered a few different options. SDFs or voxels might work, but at the time we were actually already generating proxy geometry for collisions. So we figured, well, why not just ray trace those? So we built some BVHs and we shot rays against them. There was a cool project by Jan Verbergen called CUDA Path Tracer, which implements a wide BVH tracer. So I borrowed code from that one, and to build the BVH, I used Embry, which was very simple. We eventually switched to a Rust crate that I collaborated with a little bit with Griffin on the OBVHS crate. All of the building of the thing is Griffin's. I just helped a little bit. But essentially, we now have a Rust native solution for building the BVH, which is pretty cool. Oh yeah, and we, of course, we went for software ray tracing because our hardware is potato, so we cannot support hardware tracing, and we wanted to have the same look on all platforms. But this is the proxy we actually have. They don't even have roofs, but it's kind of surprising that even with this, you can get a pretty good-looking GI if you use it well enough, if you combine that information with screen space. So now we have some kind of ray tracing. You can obviously just ship a path tracer using that because it's going to be way too slow. So we can try some approaches. Initially, we tried DDGI because that was kind of popular at the time, and I was curious to try it, where you have a regular grid of probes scattered around, and then ray trace from them and try to apply that as kind of like a mini light sources to your scene. Initially, it sounded like a pretty good idea. It meant that so we could lazily update all those probes where geometry changed, and they were stable in war space, so you wouldn't have this typical reprojective trailing behind moving objects. But it turned out that we just never got enough probe density out of it. Because the DGI has a lot of angular distribution, you cannot really have much spatial density between those probes. And we also ran into essentially aliasing issues, where if you had a small shape, you just sometimes didn't end up with a probe inside it, sometimes you did. And then visibility between them was also problematic, where you had to really constrain that. Like, I don't want the light from the inside to leak the outside. And it turned out they were still ghosting anyway, because if you had a building and then you resize it, shrinking it, for example, turns out the part which was inside is now outside, and it's darkening your outside for some reason, because it's just lagging with the updates. And because of our time of day, everything was updating anyway, so the whole lazy updating went kind of out the window anyway. So we look into another thing which was popular at the time, which was moving the probes to screen space, kind of like Lumen or GI 1.0. And the cool thing is that you end up with probes which are always sort of well distributed in the screen space, and they allow really cheap spatial filters because of the low resolution of the probes in screen space. And you end up with very little noise in the output. You can also use them for rough specular. On the other hand, they were actually very finicky this approach was very finicky to actually get to look good. So the initial results were quite promising, but to get it to shippable state would have been a bit of work. So this was the initial prototype we did. Actually, it has audio. Didn't expect that. Or something else. Never mind. Oh, yeah. So you can see it's kind of working, and it's sufficiently responsive even. But if I spin around, you can see that it's kind of flattish everywhere. And that's, again, connected to the low spatial resolution, just like we have with the GI. We couldn't have quite as much resolution as Lumen or GI 1.0 has, so we had to rely on a bit more aggressive filtering, which meant that we would somehow need to synthesize additional detail on top of it. And we still had the problem of probes getting stuck in strange places. So if you look at the tower on the left side, there's like this kind of strange dark splotches, and that happens when you actually spawn a probe in like a strange crease in between objects. So you have to do some kind of adaptive placement or trying to figure out, oh, this probe is in a bad place, let's try to get it out of there. There's also the issue of projection error into SH, and the estimate being blurry, and potentially more blurry than you would like to be. And it might look like they're both fine, but if you actually flip between them, this is the reference, and then this is the probe-based solution. It kind of looks odd, like odd lighting is slightly different than it should be, and so it kind of gets this strange metallic sheen. So I think if you spend enough time on this kind of solution, it's going to be great, but we didn't have time to polish too much out of it. And I had experience with a different approach before called Reister, so I threw away the probes and tried Reister instead. In this case, you instead of feeding probes, you feed individual reservoirs in the screen, and you get all the spatial resolution that you might potentially want, and then it's just a matter of filtering it well. And the Reister algorithm gives you really good like variance reduction and filtering via a complex chain of temporal and spatial filters, and can be very reactive as well, as you can see in the video here. However, it turned out to be complete overkill for us, because it turns out that our mostly outdoor scenes are fairly low in variance, and we actually, when implementing that, we could actually get away with just using the temporal part of Reister, and we didn't really need this fancy sample validation either, because the lights in our game don't really flicker, so they don't need to be so reactive. And turns out if you use retur without the S for the spatial part, it's actually less sample efficient than using brute force, because you end up generating some samples, then if they don't win the reservoir battle, they end up not contributing at all. And therefore, we went to just full potato GI mode, where we just ray trace a bunch of rays in the hemisphere and throw it at the spatial temporal filter to clean it up. And that's a very roundabout way to arrive into something that's actually quite simple, but it just wasn't very obvious from the start that the simple thing would work. And so there is some devil in the details in how the spatial temporal filter actually has to work in order to extract all of the detail and stability out of very sparse traces. So in terms of what you actually do, and not just the journey to it, we ray trace at 1/4 the resolution. So we have 1 ray per 16 pixels in the screen. We start by ray marching, and only when that ray march fails, when it goes behind geometry or off screen, we switch to ray tracing. Even at the end of that, if it hits something on screen, we use the radiance on the screen so we can kind of hide the fact that we have very potato proxy geometry. Then once we have calculated that quarter as ray trace data, we project it to spherical harmonics, the SH2, so 4-component per channel version of it. And then we do that in a spatial filter, which uses 8 of the quarter resolution trace outputs, which already pre-filters some of the data and kind of reconstruct it at a higher resolution already. Then we denoise in spherical harmonic space a little bit like a Metro does, and then we evaluated spherical harmonics in screen space by, once again, using a small spatial filter in a cross bilateral to sample the SH data. And for that, we use the hallucinated zonal harmonics to actually calculate the final gradients given discrete normals. And the denoising is actually quite simple. It's based on the fast denoising with stabilizing recurrent blurs from Dimitri Zan. I'm not sure how to pronounce, but essentially it's a filter which kind of feeds into itself and fine-tunes itself to use as little of a spatial filter as possible, which is kind of similar to, I forget the name, whatever. The whole pipeline is made of 3 passes. In the first pass, we generate new ray trace data, new samples, new radians, sorry. Then in the second pass, we combine this new generated radiance with previously generated radiance in the reprojection pass. If the reprojection fails, we do a gap fill. If the gap fill fails, we actually embrace race conditions and sample from the same texture that we'll otherwise be outputting, and doesn't really matter in this case. So after that, we just do a small spatial filter on top of it, with actually a very small kernel, because then when you recurse the whole thing into itself, that kernel grows in a kind of conical shape and still gives you very good denoising power. And the style stabilizing part of the thing means that you actually count how many samples you have accumulated, and then if the sample count is low, use a large spatial filter, and if it increases, you decrease and therefore tightening the GI. And as an additional twist, we also use SSAO as a cross-bilateral filter, weight in the denoiser. And to illustrate that, we start with SSAO generated by Intel's awesome XeGTAO kernel. And this is what you get if you just apply vanilla denoising. And if you use SSAO as a kind of filter guide, you can sharpen the denoising in the corners where you kind of know that you don't want to blend samples because they would be rapidly changing. And then we apply the SSAO on top as well, and then we calculate the final image. And then in terms of why do we combine this additionally with SSAO? Well, we found with like comparing to reference, kind of how I mentioned before, you always want to have a reference mode that you can see whether what you're tweaking is moving in the right direction. And it turned out that we are just missing a little bit of that additional detail, but it's like SSAO times like 0.2 or something, so it's very tiny. And in this case, our reference mode is actually not really ground truth because it also just uses ray marching in screen space. We don't have like full RTX mode in the game, but it is still better than nothing and quite sufficient for what we need. Because what we're after is creating the same kind of general impression in the lighting and not matching it bit by bit. And I think a lot of the error is actually due to the SH projection rather than other sources. It's good enough for us, at least. But now that we have ray tracing, it'll be a shame to only use it for GI. So let's do it for other stuff, but sparingly. One of the things we do is everyone's favorites, which is reflections on water. And as a water, the basic setup is that we run it after deferred lighting, so deferred rendering, deferred lighting, and then we apply water in a sort of forward-lit way. Currently, our water is fully flatland, but we have plans to extend it, so we didn't go with something like planar reflections, because we don't have the flexibility. Therefore, ray marching and ray tracing. We have some waves which are normal only, that are based on some pre-calculated textures and ripples for our floaty creatures. And then for water, we have the major components, which is refraction, and caustics. And starting with reflection, we start with SSR. And as this is a reduced resolution image, so we can see the artifacts. But as everyone knows, SSR kind of fails quite often and gives you something ugly. So we detect the ugly. In those cases, we do ray tracing instead. And to do it fairly efficiently, we start with a pretty cheap ray march with just 8 steps of linear marching combined with 3 bisection steps and 1 second operation. And then we can, in theory, just in that case, if we have a miss, we could ray trace in the same shader, but that would throw all of the occupancy of the GPU out the window because you could end up with a random collection of rays which missed and which succeeded. And we also want to ray trace at half resolution as opposed to the ray march, which is full resolution. So we write out the misses to a separate buffer, and we essentially compact them and do a separate dispatch over just those misses to ray trace it at half res. And similar to GI, was sample the screen space if the hit from ray tracing happens to be at the screen. There's a little bit of a caveat with that, is that due to the random nature of ray marching and the waves, you end up with this kind of like random peppers and salt noise where the SSR has missed. And it's kind of annoying because you can kind of just guess that will be similar, and that's we apply our little hack, and we hallucinate additional hits by just looking at neighbors in quads. And if at least one array in a quad has hit something, we just assume, well, I'm guessing like you're going to hit at the same distance. So we kind of synthesize the hit point using those, which also gives a nice benefit in that whenever misses happen, they actually happen for the entire quad, which means that we can ray trace at half resolution, which is what we wanted from the start. And speaking of the ray tracing fallback, as I've shown before, the ray tracing geometry is kind of potato and doesn't look very good. And we found that actually if you use the full lighting for it in that ray tracing fallbacks, it can look a little bit jarring, especially that the lighting on that for subsequent bounces can look a bit off because we don't have the same kind of feedback loop that we have for SSR, which or screen space GI, which can kind of feed multiple bounces just from the screen space. So the ray tracing pass has to kind of make up something, and sometimes it looks a bit too bright, a little bit too dark. And we actually found that it's better to just fall back to blackness because what you're very often after is just blocking the reflection as opposed to actually generating like proper results out of it. Maybe for a game was a theme park, it will be a different story, but in our case, stuff can be dark and looks fine. And then the waves actually break up the geometry sufficiently that you really don't notice that everything is just this Duplo land. And then in terms of refraction, that's another area where we hack and cheat. We actually tried like doing proper real refraction by bending the rays, but we actually just didn't like it because the ray foreshortening meant that the ponds and little streams looked a bit too shallow. And it also was more expensive and meant that sometimes you wanted to sample information which was not on the screen because if the ray bends a lot, you may end up sampling in places where you don't have geometry. So we cheat and we just distort the ray slightly by the waves and ripples and just ray march the distorted ray, which also means that we can get away with like a very simple ray march with just 3 taps and 2 bisection. And we sample from a copy of the depth target that contains just the underwater stuff that we captured during the early rendering. And we also have some caustics, which are complete fakery as well, by just doing some random thresholds on top of the wave textures. And then we project this strange thresholded thing onto the water using the sun angle, and just gives us something that looks good enough. Speaking of water, let's talk about the solid part, and that is our ice. Ice is a very similar setup to the liquid water. Also runs after all the deferred rendering, but now it's a bit chunkier, a bit more involved because the reflection and refraction needs to be rough now. So the surface pass additionally also needs to calculate diffuse lighting and diffuse shadows. And we have seen before, shadows can create this kind of blocky temporal aliasing. So this pass also internally calculates the shadow TAA, which means that like one of the outputs has to actually be just the shadow map itself. And then in addition to that, also generates a bunch of data for the deferral of reflection and for the deferral of filtering of refraction. And we try to defer all the things so we can actually, once again, reuse all the samples and synthesize detail from very few rays. And then we throw the whole thing at spatial temporal denoising and the reflections and refractions. Starting with reflection, so we ray march, again, in a deferred pass, half resolution, I guess half resolution depth. We're using spherical cap GGX sampling with a heavy bias of like 70%, I think. So we kind of cut off the edges of the GGX cone. We use a fairly a bit more detailed ray march this time because we found out like we just want a little bit of extra definition by like a little reed sticking out of the ice. Then once again we compact the misses. We dispatch a ray trace over just the misses. But then instead of just directly outputting gradients, we do this dance kind of similar to the stochastic SSR technique I presented previously, where we generate we gather all the hit data and then we kind of synthesize how the hits look like if all the samples shot multiple rays. And we tried using the fancy ratio estimator, but found that in this specific case, a simple cross bilateral over roughness and hit distance was sufficient. And one thing which really helps a lot is using the kernel radius for this filter based on the projection of the lobe of the BRDF, which means I can blur at just the right scale. That's the you would actually get the kind of blurring you get from the stochastic process. And the refraction, we seem to really hate the proper refraction, so we hack it here again. We just take the BRDF lobe for reflection. We flip that and essentially do a reflection upside down, which turns out to be good enough for us again. And once again, it's a very puny ray march, which is very cheap. And then we throw that at the denoiser once again. Here, the refraction is at full resolution, but we still want to denoise spatially. And this is also, once again, using the projection of the BRDF lobe, which is why it's helpful to actually just use a simple reflected refraction, because then that lobe is simpler than for refraction. And we throw that at a temporal filter together with the reflection data, and that one's pretty simple. We actually get a bit of ghosting here, but doesn't really matter because everything under the ice and top of the ice is a bit blurry, and this one specific case is fine. So this also, the spatial resolve ends up serving as a temporal filter for everything. That's mostly it for ice, but we also have this cool feature that's under the ice, that's cracks, and it looks more than actually is. It's just a bunch of meshes with some fakery in the normals, kind of point them at the light source, make them all catch light always. And then if you throw that at our blurry refraction, they look pretty cool together, especially with the Beer-Lambert absorption that happens with it. And speaking of blurring things, depth of field. So that's something we have invested quite a lot of effort into. But we've started quite simple, actually. We started with not really knowing what we want to do with DOF, and we just plugged in this cool single-pass shader from Dennis Gustafsson, which is awesome for its simplicity, but also has this kind of peculiar artifact that sometimes you get features that are a little bit too sharp in the foreground, and it doesn't really make much sense. But we actually considered that to be a bit of a feature initially, because we didn't really know whether we're going for like optical effects or kind of painterly effects. We generally try to treat the frame as a painting. We're not aiming for photorealism. In this case, we're kind of inspired by Studio Ghibli and how an artist might just use coarser brush strokes in the background and essentially have this same-ish amount of detail in the foreground and background. So we kind of like this simplification it was doing. So for some time we stuck with that, but eventually, like a proper optical depth of field won over because of one important feature, that was tilt shift. Because we use a little bit of a, we call it squee-driven development, where you try to maximize cute aggression. And it turns out if you have this like cute little diorama and then you turn on tilt shift DOF, and everything looks even tinier, you just have this like reaction, and that just was sufficient to completely win over and move to a proper optical effect. But for that, we needed to fix the artifacts. And I have to admit that I don't really actually understand DOF, at least the way it's presented usually in graphics literature. I kind of get the path tracer optical part of it, but this kind of diagram is what comes to my mind when I think of DOF from Jorge Jimenez. And I like the diagram, I think it's cool, and I can understand how each point kind of increases into a little disk based on its circular confusion, but I don't really understand how they should be occluding each other, or why just like changing the slope slightly means that they blend against each other in a different way. The original paper suggested that you can do brute force by sorting all the samples, so I tried to kind of treat it as an OIT problem, throwing a bunch of OIT algorithms at it, but I couldn't really get anything cool out of it, and I still really don't buy that it works. But there's a classic thing which does work, and that is you just jitter the image from multiple viewpoints, and you use an accumulation buffer to generate a single picture out of like hundreds potentially. And then we can also do it a bit quicker by synthesizing those additional viewpoints, by just doing a parallax distortion on top of the image you have generated, and then filling in the detail. However, we can only generate one image, so our options are limited. We have to do pretty fancy reconstruction to do that. But I have tried a whole lot of things. I tried, like, I think, have a giant DOF Hageless file which had like 10 different algorithm implementations, and this one specifically about trying to synthesize the views. I found the whole thing to be really difficult to actually achieve, and in general, like nothing really worked well, and it doesn't seem like there's any algorithms that handle foreground defocus well and actually run in real time. So I kind of came back to the drawing board, and I figured, like, okay, is it even possible to extract something cool out of screen space? And so what would a path trace version of DOF look like, but using ray marching instead? Because that's how I solve all the problems here. So I simply use the ray marcher by tracing tons and tons of rays in the same way that a path tracer would. So you sample additional points on top of your sensor/aperture, and then you kind of mirror them around the focal point, and you can actually get an image like this. So it turns out that there is a lot of information in screen space that you could use to get pretty good foreground defocus. However, this was super slow. It was crashing all the caches and costing like 100 milliseconds on a chunky GPU. So it needed to be sped up. But if we look at from the front and consider just the different arcs of the radial DOF kernel, and if you see what kind of rays we trace within just that one slice, they all kind of trace similar information. They end up sampling the same points over and over again, which means we can prefetch a bunch of data and reuse information between them. So what we do in the shader is that we work in those 1D radial slices of the kernel. We prefetch all of the COC/depth. Well, you can prefetch deep depth values if that's what you work with. We prefetch those COC values into local data share, and then we calculate all the intersections. So for each of the rays and each of the slopes, we essentially find O n times m intersections. The math ends up being very similar because within a single slice is just the slope of the ray changing. So it's just a little bit of like extra division per intersection. And we store per each ray, has it intersected with the surface yet for each of the steps that we take the ray marching. And we start as a ray mask, as a bit mask for each of those ray slopes in VGPRs. And then finding the actual intersection points is just like first bit low, first bit high, and then you can find out which is essentially the first intersection. And then we can also refine that using a second test. So now we have a way to do bulk ray marching. And it's essentially still the full ray marcher just optimized. So we can do a fun thing of visualizing how individual sub-rays of that work. So you can actually see that this is quite similar to the accumulation buffer approach, but all of those views are just done by ray marching. And so we get enough precision out of that little test and the second intersection. So the camera is not moving here. I'm just nudging which ray is being visualized. And if you combine them all, you get DOF, essentially. So I guess we're done here. And this works. Right? And then we get this. It's like, what is even going on here? So I thought I had something cool and it would work, but then artifacts appeared yet again. And this edge case was initially a bit difficult to find, but appears because that's pretty basic background reconstruction. When ray travels, we just use the last hit point that actually saw if it travels under the surface and use that as the color. So on the left side, you can see that this essentially causes kind of trailing artifact behind objects where you don't have information, which most of the time is actually fine. But in this specific edge case, when you have multiple rays coming at different angles, so different of those 1D slices going behind the surface, they all end up having the same point. They all use the same fallback. And that's you end up this kind of sharpening just next to an edge. And you can see that by just showing different angles of that 1D slice. You can kind of see like something is rotating around those singular points that previously were sticking out. And the sad thing is that I actually don't know how to fix it yet properly, at least not in a way that will be performant, and we have a sort of a hack. So what I found works sufficiently well for us is that when you actually find that intersection point, you can see whether it's actually close to what we were trying to initially intersect. So you were trying to find an intersection close to the focal point, and if that point you have actually found is somewhere far away from the focal point, it means the ray has traveled under the surface, and your intersection is actually not accurate. In that case, I assume that, well, it will be a blurry something. Therefore, I fall back to just a pre-blurred version of the background that the shader does just alongside of all the calculations. And I haven't really had time to figure anything smarter, but this is sufficient, at least for us, because this artifact is still pretty rare, and you can still get pretty good results out of it without any of the typical aliasing issues, or like seeing where each layer of the DOF splits up from the others, and you can get something quite creamy. And you can also throw typical optimizations at it, such as analyzing content of the image. So we detect, for example, which of the tiles can be done at half resolution because of the low COC variations within there, which parts need to be done with full detail, and which can be simplified by just doing a simple background gather, kind of like the Unreal 5 presentation. And we're also going to use MIPS to pre-filter some of the data and get rid of some of the sharp hotspots and noise. But it still is not free. It's not as sample efficient as some of the other approaches. Works for us because our dynamic range is fairly low, so we don't have any like super hot highlights in the background like some sci-fi games might have. So for us, it's fine. But in practice, if you try to use it for a game with like very intense HDR, you might find it's a bit undersampled. So it might be a bit of a situational thing. And in practice, for us, we just throw the resulting noise at TEA, and then at least in our case, it works. But in other cases, it might give you the typical ghosting. And for us, it runs in roughly 1.3 to 1.5 milliseconds on a 2080 at 1440p. So it's sufficient, at least. But in photo mode, we also like crank up the settings, because when you actually have the full tilt shift, you need a few more samples to properly resolve it. But to illustrate what we can get out of that, this is the version that was costing 100 milliseconds, and this is the version costing 1.3 milliseconds, which actually looks slightly better on some of the edge cases, because you can see some of the pinching is gone, but otherwise it's actually the same thing. In terms of code, I was going to prefer like a nice version you can plug into your code, and it might come soon at some point, but I just like essentially copy-pasted one of our shaders and dumped it into Gist, so if you want to grab it. It will not work straight out of the box, so you might need to do some messaging, but at least like some of the ideas are there. You can just use it as a basic reference. And doesn't have any of the fancy multi-resolution stuff, so it's going to be slower than the version we have right now, because that requires quite a complex pipeline, multiple compute shaders, analyzing all the content. Since we're moving down the graphics pipeline, or to the end of the graphics pipeline, let's talk about image formation. So you have generated a bunch of R, Gs, and Bs using all fancy lighting, fancy post-processing, and so on. But how do they actually form an image? There's a bit of a discussion or debate about that. Do you model human perception and try to kind of synthesize something that a human would see when looking at the picture? Do you try to go after photography and film? But in practice, rendering is its own art medium. You can do whatever the heck you want. It's eventually all about evoking some kind of perception in a human being. Just make sure to use actual conscious choices and not fall into traditional traps. And one of the traps you may fall into is this notorious 6 problem, where if you apply a pair-channel tone mapping curve or display mapping curve to your image, you will most likely see those 6 colors popping up everywhere. And at the bottom, you can see just clamping the colors. You can see applying Reinhardt and the typical ACES curve. And the right side of it, where exposure increases, is always the same. And the only thing which is special about these colors is they are corners of the sRGB cube. So if you see that in your pictures, it's not something you actually made as a choice. It's just something that is an engineering choice of the color space that you're using. To deal with that, we use a display mapper that's, this is a shameless plug, but I made a display mapper kind of around the same time Anastasia was starting on Tiny Glade called a Tiny Map Face, and it is designed specifically to avoid this issue. So instead of kind of allowing the colors to saturate to the extremes of the sRGB cube, instead it shifts towards white using a path to white, which I consider to be fairly neutral, but the whole thing is generally kind of opinionated and might or not work for you. But in terms of how you actually will plug that in, it's actually a very simple 3D LUT that you apply after Reinhardt, and it's just kind of can fix your colors potentially. There's some caveats in that it only works with sRGB color. It doesn't do HDR output, at least out of the box, and it is subjective to tune to my specific preferences. But if you want something a bit more neutral and with similar characteristics, you might want to try AGX by Troy Sobotka, which has some of similar characteristics. And just to illustrate some of that in pictures, this is what happens if you just take the HDR values, the tri-stimulus, and you clamp it. You end up with this lovely yellow color that has been dubbed rat piss, which shouldn't be there, because if you just reduce the radiance values to levels where they don't clamp, it actually doesn't have this yellow. But if you apply everyone's favorite ACES, you have this yellow as well. And even if you use something fairly gentle like the Reinhardt operator, you still end up with this kind of like shift towards this kind of sickly, unsaturated, strange colors. And if you apply Tony McMap face, you actually get something that kind of resembles those original colors, at least to some human perceptual systems. And that would be it. I think we have like maybe 3 minutes for questions. And so thank you so much. Thank you. And if we don't have enough time for questions, just catch me afterwards, and I'll answer everything.
Okay, please raise your hand, and I'll come by.
Thank you for the presentation. It was very interesting.
Thank you.
So you've worked with Rust, right? What made you decide using Rust over C++, and how was your experience working with it?
So for our game, I don't really imagine using anything other than Rust, because it is simple at the surface, but under the hood, there's lots of very complex chains of operations. We support things like infinite undo redo with animations, and all of those generators have just dozens upon dozens of systems that will be kind of a nightmare to keep track of. All of the generators are also fully deterministic, which means that we need to have this kind of precision that Rust is really famous for, and so this kind of harsh control. So some people might see using Rust as an impediment of iteration. We actually kind of see it as a prerequisite, and we haven't had a single memory corruption-related crash in the entire development of the game, and that's not something I'm familiar with from C++. So in practice, for us, using Rust has been an absolute blast, and we also found that you can get stuff rolling very, very quickly by using the crates ecosystem. For example, we use the ECS from the Bevy engine to run all of our gameplay logic, and there's a whole bunch of crates for all of our pipelines, processing, backgrounds, and window interactions, and so on. So it's kind of really a superpower. I'm used to just writing everything from scratch, but in Rust, you just collect crates quickly, move on, then rewrite what's important, and it's really a refreshing experience.
All right. Any other questions? Please raise your hand.
First off, great presentation. The passion comes off immensely, and you're quite good at explaining concepts. I was kind of curious about your experiences with Restir. You mentioned that you felt that Restir GI was a bit overkill for your applications. First, I'm curious why that's the case. Second, you mentioned you were doing some experimentation with the Restir DI. How's that been going?
So for Restir GI specifically, it's overkill for our case because the game is still mostly outdoors. Some people are trying to kind of hack it to be indoors as well, but simply because of the softness of the sky and the sun, well, sun is not very soft, but because of this presence of plenty of light outdoors, if you don't have lots of local lights, your variance on the input and on the Monte Carlo process is actually just very low. And you don't need a lot of denoising machinery to deal with that. And when you're doing Monte Carlo style GI calculations, what you're really doing is just dealing with variance. So you have some kind of way to sample the irradiance and some way to filter it. And Restir was just too much for our needs. And so it comes with some fixed costs that we need to run to do the reservoir exchanges. And those are just like a little bit too much memory traffic for the potato devices that we try to run the game on. So in the end, just wasn't a win. It would have been fine, but we didn't need it. That's it. In terms of Restir DI, I have really only just started tinkering with it because we currently have a silly limit of you only get 32 light sources. If you place additional ones, they don't really cast light. And that's just a silly hack that we had to have to actually ship the game. But I'm looking into using something like a light tree to accelerate the sampling of the lights and then to throw that at Restir DI to actually do allow pixels to talk to each other and figure out which samples are actually relevant to their lighting. I have done some early tests. They're still a bit too noisy for my taste, so I'll just be tinkering with it. It's mildly promising, I suppose. But still, I end up having a little bit too much variance from the initial test than I was anticipating, so it hasn't moved on very quickly yet.
All right, we have time for one more question. First of all, I just wanted to say it's a really great game and a really great presentation.
Thank you.
I'm just curious, when you're doing path tracing, how many bounces do you do? And do you also do maybe a radiance cache?
So for path tracing, the only real path tracing we use in the game is for the reference mode. And then we just have something like 3 bounces because once again, because of the outdoor nature, we don't need more. But for the game itself, it's not path tracing per se. It's more like, I guess, a single pass of final gathering. Is that we just shoot rays out, sample radiance, and feed them back. But there's a temporal component, which means that you essentially get infinite bounces from it as well. So that's essentially that. It's not really path tracing.
All right, thanks, Tomasz.
Thank you.